Alrighty, in this video we are going to be talking about the mean value theorem and Rolle's theorem. We haven't talked about the mean value theorem as a definition in class, but we've done these types of problems where I ask you guys to find out when the average rate of change is equal to the instantaneous rate of change. We actually have a definition for that, aka the mean value theorem. So you already know what this is. One important thing to note is that f needs to be continuous and differentiable for the mean value theorem to apply. Graphically, this is going to look like what it says, where the instantaneous rate of change, the instantaneous rate of change is equal to the average rate of change right here. So that is when we are parallel. Very cool. Because they have the same slopes. Very cool. Rolle's theorem is just another special case. That's just whenever we have the average rate of change being 0. Therefore, we have a horizontal tangent line. So your derivative is going to be 0. For number 1, we're going to do this algebraically. So we want to find the value of c on the interval 1/2 to 2 that satisfies the mean value theorem for f of x is equal to x plus 1 over x. One thing to note is that f of x is undefined at x is equal to 0 because of our vertical tangent, vertical asymptote at x is equal to 0. But lucky for us, because my interval is from 1/2 to 2, we don't have to worry about that. I'm also going to rewrite this so that f of x looks like 1 plus 1 over x. That way, whenever we take the derivative, I don't have to use quotient rule, and I can just use regular power rule here. The first thing that we're going to do is find the average rate of change from 1/2 to 2. So if I find f of 2 minus f of 1/2 over 2 minus 1/2, f of 2 would be 1 plus 1 over 2, which is just 3/2. And then f of 1/2, 1 plus 1 over 1/2, 1 plus 2 is 3. 3/2 minus 3 gives us negative 3/2. 2 minus 1/2 is also 3/2. So this tells me that my average rate of change from 1/2 to 2 is negative 1. Now my instantaneous rate of change, I'm going to find the derivative of this. And since I want to find the value of c, I'm going to take the derivative with respect to c. Well, I'm going to change all of this to be c's. So 1 plus 1 over c. So then I get c to the negative 1. If I take the derivative of that, then f prime of c is going to be negative 1 over c to the second power, since it is the same thing as saying negative 1 c to the negative 2. So just put it in the denominator. Now, if you want to keep it as negative 1 c to the negative 2, that's fine, if that's simpler for you. So now what we're going to do is go ahead and set the average rate of change equal to my instantaneous rate of change, and then solve her. We'll get negative c squared is equal to negative 1, c squared is equal to 1, c is equal to plus or minus 1. Now, on the interval 1/2 to 2, you'll see that only 1 will work, positive 1. Negative 1 will not, because it does not fall in my interval. Graphically, it looks like this right here. So we have our red graph, which is our original function. We have my purple line, that's my secant line, that's my average rate of change from 0.5 to 2. It's negative 1. And then you'll notice that my instantaneous rate of change at x is equal to 1 here is negative 1, which is what we want to try to find. So that's why c is equal to 1. So that's what we're trying to figure out, the c value, or the x value, where my instantaneous rate of change is going to be parallel or the same because of the same slopes to my average rate of change. For number 2 here, we're just doing the same thing, except this time we have a weird function. You'll notice that this is going to be a polynomial, and we know that polynomials are going to be differentiable. Sine is also differentiable. So because the polynomial and the trig function sine is differentiable, f of x is going to be differentiable and therefore continuous. We're going to use our handy dandy calculator to see the c value in the open interval 0 to 2, such that the instantaneous rate of change is equal to the average rate of change from the closed interval 0 to 2. I have already put my function into y1. Make sure that you guys are in gradient mode. And under y2, I'm going to put my average rate of change. So I'm not going to solve it by hand. I'm going to let the calculator do it for me. Alpha trace y1, alpha trace y1, 2 minus 0. And then for y3, I'm going to let that be my instantaneous rate of change. But before we do that, I got to find out what my derivative is. So I'm going to go to math 8, alpha trace y1 to denote that I'm taking the derivative of y1 with respect to x right here. So x is equal to x, which just gives me the derivative function. I'm also going to unclick y1 just because we don't need her. I only want to see the average rate of change. That's going to be as a line. And then I want the derivative function, y3. I'm also going to change my window from 0 to 2 because that's what my bounds are. I might change my ymin and ymax if I can't see it in terms of what my graph is. Okay, yeah, I'm definitely going to have to change that. I'll change it from 0 to 1. Looks like nothing's negative. So 0 to 1. Okay, there we go. So you can see that we have 2 intersections where the instantaneous rate of change is going to be equal to my average rate of change. So I'm going to go to second trace, intersect, and find out where my intersection is. So my first one is going to be at it's the first one. My first one's going to be at 0.74051. So you're going to write that down. And then my second intersection is 1.74166. And of course, just as a FRQ reminder, make sure that you're giving me at least 3 decimal points for your answer. So C is equal to 0.7405, and C is equal to 1.7416. All right, so for number 3, we're looking at Rolle's theorem here. So at this point, we are just setting the derivative equal to 0, because that's what Rolle's theorem is. And we want the integral from -1 to +2. Since this is a polynomial, f of x is differentiable, therefore f of x is continuous. And at this point, we can just take the derivative of this, which is an easy derivative for us to take, and then set this equal to 0. I'm not going to do that, but well, in this case, C. So C is equal to 1.288. So there's one value, in this case 1.288. Sometimes on the multiple choice, it might ask you which of the following functions will mean value theorem not be applied or cannot be applied for. So looking at number 4, we have f of x is equal to the absolute value of x minus 1. This can't be applied because x is not differentiable at 0. Because x is not differentiable, or f is not differentiable at x is equal to 0 because of a corner. So Rolle's theorem cannot be applied. Likewise, for number 5, why can't the mean value theorem be applied for this? -2 to 2. Well, we could see that we have a vertical asymptote at x is equal to 1. So we have a vertical asymptote. Now, can we change the intervals so that Rolle's theorem can be applied, or mean value theorem? Yeah. So for number 4, I could probably do, I don't know, like 0.5 to 1. Or for number 5, I could do 1.5 to 2. Or something like that, where every interval or every value is differentiable and therefore continuous. All right, and then sometimes you might be given a table of values. So in this case, we are given this table right here. And we want to see for which the mean value theorem guarantees that f prime of c is equal to 6. So we want to see when the instantaneous rate of change is equal to 6. So we want to look at the average rate of change here. Now, if you look at this, there's going to be 3. Figure out what those 3 are, and then play back the video. All right. From 3 to 5 is one of them. So in this case, 18 minus 6, 5 minus 3, 12 over 2 is 6. So 3 to 5. We also have 5 to 9. 42 minus 18, 9 minus 5, 24 over 4, so that's 6. And then we also have 3 to 9. So 42 minus 6, 9 minus 3, 36 over 6. And all of them will give you 6. All right. In the next video, which you'll have to watch, we'll talk about extrema.